Hello and welcome back. We now discuss a possible solution to our next regression exercise on the public dataset California housing that was first described in this paper. The data are about, unsurprisingly, the house prices in California, and we notice that the target variable is a natural logarithm of the median house price, so not directly the house price itself. But mainly, we want to use this example to explore how we can use hierarchical features and build a model pipeline in scikit-learn. So this can come in handy because different types of features will require different types of preprocessing. We can often build a much more powerful estimator if we exploit known behavior in the data. So we import our standard libraries. We notice that we can fetch the data set already using a convenience function within scikit-learn, because this is one of the more popular data sets. And we also notice that we import a few classes that we normally don't use in simple models. And as a regressor, we use the modern His-gradient boosting regressor. This is fairly new and very performant. It's one of the recommended go-to methods if we just use machine learning on regression classification datasets. There's an equivalent one for classification. Because we are here in the solution folder of our repository, we have a quick hack to access the models from the parent directory, but you don't normally do this if you don't need. So first of all, we can access the data. We can use the fetch method. We've done it here, and we load a local copy to avoid the internet traffic and look at the data. So we have an unnamed column here, which is just the index, and then here there are the variables, the features. So we notice that we have, for example, latitude and longitude. So this relates to where the houses are located. First of all, these unnamed one we can drop because this is just the index and we already have an index as part of the data frame. We can do some descriptive statistics like mean, standard deviation, and the most important quantiles, and now start with our exploratory data analysis. The median house value, this is the target variable that we need to predict. And we can see that the value of the house is, as we said, first of all, the logarithm. So that defines the range, but we also observe this big peak at 5 here. So this will become important later on when we start building our model, and we need to think about what we do about this. And then we have a large distribution which is skewed and not symmetric. So we can see that most house prices are maybe not too expensive, or we have a large tail to very expensive houses. And this peak essentially means that everything that is very expensive is no longer associated with a number, just and lumped together in this one bin. So we look at a few other variables, for example, the median income, or the average number of rooms. And here we plot this on a logarithmic scale to see the long tail. So most houses have indeed not that many rooms, although you can argue that maybe an average number of rooms of maybe 10 is quite substantial already. But we also see that we have a few houses with more than 100 number of rooms. So this in our real life would now back the question, how does this come about? Are these real houses? Because we can't influence this data set or inquire about it. We need to treat them as they are. So that could either be a problem in the data, an outlier that was added through the data acquisition process as a fake data, or it could be a real data set. For example, it could be a large hotel or convention center. They would have that many rooms. At this moment, we simply don't know, and we also don't have any means of inquiring. But if we were to be a real data scientist in a live project, then we need to find out what's happening in this area. We can also look at the average number of bedrooms. So we see the same thing. So there are houses with more than 30 bedrooms, although of course most will only have a much smaller number. Here again, we would have to inquire if we had the chance of finding out what these houses are about. Now we look at a few relationships between variables, for example, the median income and the population. And you can see the behavior here. The color coded, we have the house value. And we remember that we have latitude and longitude. So if you put this as a scatter plot and put the hue of the house value, our target variable, in there, we can see that we can get back the outline of California, and the dark points correspond to very expensive houses, and this is probably what we would expect. So here are the large suburban areas, San Francisco, Los Angeles, and near the coast are the more expensive houses, and here in the deserts there are also houses, but they are not quite as expensive, and in between there are not many houses either. So now let's start to build our machine learning model. Again, we follow the typical scikit-learn approach of creating an instance of our model, fit and predict. And in this example, we use the His gradient boosting regressor as a modern machine learning method that is very performant, more or less out of the box. First of all, we need to define the training columns and the label. And the label is again the last one. So we split our data frame into X and Y, and split then this into test and training data. Define our model and just use the default values for now. Fit, copy over the data frame of the test data, make the predictions, and append the true values and the predictions, so we have them side by side and can compare how the model performs. Now we plot the distribution of the predictions and the true values with some global metrics. So first of all, we plot the distribution of the prediction itself, and we can already see that it's not too bad, but obviously not well enough. The sharp peak is not captured by our model, and there's also a considerable shift. So let's try and see how we can improve our model. First of all, before we do this, we look at our residuals, and we can see the sharp peak again, but the residuals themselves are not too bad. They're scattered around the 0 line, which is what we want to do. The profile plot itself is also fairly okay, so we don't see any obvious issues, but we do see one here. So this, again, to highlight, makes it important to really look at the results in multiple ways to capture where we may or may not have issues. For example, if we were just to look at the profile plot, we would not have spotted any obvious issues. If we look at the residuals, we can see there's an issue here already. It becomes much more apparent if we look at the distribution of target in the test data and the predictions. Now, we want to move on to feature engineering. So how can we improve our model? We've seen that we have the latitude and longitude, but we haven't included that in the model now. Individually, these variables will likely not be very helpful because the model has no way of knowing that the two variables, latitude and longitude, belong together. Of course, from our everyday experience, we know that this is the case, but it will be quite hard to teach this to a machine learning model. So this is where our expert and domain knowledge comes in. So the best way to make use of these variables is to have a simple model beforehand. So we have as input latitude and longitude and train it again on the target variable. If we remember the map from upstairs, let me scroll up for a bit, we can see, right, this is already quite predictive. Latitude and longitude is already quite well related to the house price itself. There's a clear correlation between them. So we take a very simple model to capture this. So to do this, we need to add this simple model as a feature to our data frame later on. So this is how we do it. We define a class and say, okay, we just use a simple clustering algorithm between those two and want to add them as a feature. And we need to inherit from the scikit-learn method here, from the base estimator. So as with any class, we need to have the special method for initialization, and we give it the parameters, the columns we want to have, and then we need to create an estimator, and here we want to use nearest neighbors regressor with these hyperparameters. And now we need to implement the fit method. So this is really that we have the data with the columns that we give it, right? This is the parameter we give it, and we call the fit method and return the object itself. And because we pass it through, we don't need the predict method as such, we need to sort of append the output of the predict method to the data frame so that we can pass it on. So essentially what we want to do is we have an input data frame, tell it that here we have the latitude and longitude as the new variables on which this clustering algorithm is run, and then the output of this model should be appended. So this is what we do here. We call it transform because we transform the data. This is one of the scikit-learn parts where we say we do a prediction, but we also pass it through with the data that we get. And here what we do is we call our estimator with a prediction on the columns that we have, and now add a new feature variable and append this and return the data. Now we continue as we had done before. We have the training columns and the labels. We split this. We define the columns we want to work on with this estimator, latitude and longitude. Right? Implement an instance of this class which we have just defined with the columns we want to operate on as a parameter. And now we use the scikit-learn pipeline. So the pipeline tells scikit-learn that we use these things in succession. So first of all, we have the k-nearest one. This is our instance here. And then we have the model. This is the his gradient boosting regression. And instead of then calling model fit, we fit the whole pipeline. And as you can see, this is a fairly neat way in scikit-learn to chain different models together. And so the data runs through the k-nearest, is passed through, we append the new feature, and then this is passed into the model. You can visualize the pipeline here. Data comes in first through the k-nearest as a feature class, then to the his gradient boosting regressor, and then it comes out, and then we can proceed as we did before. We make a copy of our test data, make the predictions, append this to the data frame. And then we look at, again, the metrics and, again, look at the performance of the model. We can see that still this peak isn't captured, but the distribution is now much better behaved than before. You can also look at the residuals. Compared to before, they are indeed a lot flatter, so this is better. We have here this arch effect, which is the line at 5, and the profile plot is good as well. Now this leaves us with a final issue. Let me scroll up here. We haven't captured this peak. One way to proceed now would be to split this into a classification and a regression task. So first, remove the data that is in this peak and make a classification project out of this and classify, is this a very expensive house, i.e. is this a value of 5 or lower? And then for all the remaining data, predict the shape of the his gradient boosting regressor, and we can see that this will work quite well.